In today's lesson we're going to look at intersecting planes. So to look at intersecting planes, what we're going to look at is lines and points and how they relate to one another. Then we're going to look at dihedral angles, how to find them. Then we're going to look at two planes when they cross over one another, and we have to find the line of intersection first, and then from that we'll look at dihedral angles. In the second lesson we're going to look at skew lines, so we'll skip that for today and we'll move on to some exam based questions based on intersecting lines. In this lesson we'll look at basic higher level questions, and in the second lesson we'll look at some more complex questions that could be asked on intersecting planes. So to start off here, what we have here is we have the horizontal plane, we have the vertical plane, and we have a line that is drawn in this space here. Now what we have here is it's projected onto both planes, so we see two different views of this line here. This is the elevation view, this is the plan view. Now if we introduce two more edges, we create this triangular surface here, which is called a lamina. So a lamina is this surface here that is created using three lines. And so it's a triangular section here that floats in space. It's got no thickness. Now we're projecting the elevation and then the plan view of it. Now in this question here, based on a line and a dot, we need to find the shortest distance between this point and this line. Now what we have in this here is it is not possible to just draw a line from P straight to this line here and a line here, because we'll get two different answers. So imagine if we drew a line 90 degrees here, we'd have a point here where I have the cursor. Then if we did the exact same thing in plan, we'd have a point here. Now them 2 points wouldn't correspond with one another, so we have to look at this differently. So first we need to see is a true length of this line AB. So to see any true length we need to look in it at 90 degrees. So what we're doing here in plan is looking here at 90 degrees, setting up our x1 y1 line parallel to AB in plan, then marking off our heights 90 degrees and getting our heights then from our elevation. Now what we have here is we have a true length. Now we project down where point P is. So point P is now positioned in this location here. Now we still are not able to draw a line from point P to this point here, because the reason for that is we do not know if point P is directly over the line in this view here. So we need to look along this line here and see it as a dot. So this is a true length, so we're going to look along this true length here and see it as a dot. So again we look up along it, create x2 y2, look up along this, find our dot. So that's our dot AB. Then we have point P here brought up. Our distances this time are got from the previous XY line backed away. So to find position of AB, we went to our previous XY line and measured backed away. Then the same to find point P. This is previous XY line measuring backed away to find the position of point P. Now what we can do in this case here is we can draw a line from P to AB. So that's our shortest distance, that distance there. So that answers this question here: what is the shortest distance between AB and point B? Now in this question here we are given a triangle or a lamina in both an elevation and plan view. What we need to do in this question, and it is asked quite often in exam questions, is how to see the true shape of this surface. So to find the true shape of this surface here, what we need to do is draw a true length across the middle of it. So what we have here in this view down here is we have a 3D representation. So what we've done here is sliced across this plane. So we sliced across this plane, creating this green edge here. So this green edge, drawn in elevation then from C, if we bring this down to plan and draw it in plan, we know this is a true length in plan. And the reason it's a true length in plan is if a line is horizontal in elevation, it's a true length in plan. So in this question here, we now have a true length in plan, and anytime we look along a true length, we see it as a point view. That means this point view is on this surface here, so we'll see this surface as a line. So what we're doing here is another line taken across to prove the same thing again. This would be a true length as well. So if we go with the original true length here, look up along our true length. So what we can see here is in the 3D graphic here, we're looking along this line here. So when we look along this line here, we're seeing this triangle as an edge view. So we're looking at an edge view of this triangle. So if we project up the true length, again, x1, y1, 90 degrees to our true length line. Getting our heights now from our elevation. And if we've this done correctly, A, B and C should join up in one straight line. If they don't on your drawing sheet, you have some error regarding measurement. These need to line up. Next then, we have ABC as a line. Now the next, what we're asked in the question to do is see the true shape of this. So the easiest way to see the true shape of this, once we have it in an edge view, is look at this at 90 degrees. So the red arrow here shows if we look in at this at 90 degrees now and draw our second auxiliary in this location here, we'll see the true shape of this triangle. So what we're doing here is we're setting up a datum line here. The reason for a datum line here is there's a lot of space here that's not needed. So what it means here is we can cancel all these measurements here, because to find measurements in the second auxiliary we go back to the previous xy line and measure back the way. But we're measuring back away this distance, so we want to get rid of this distance. It's not really any need to have this distance, because what will end up having if we have this distance is our auxiliary will be nearly off the page. So we can eliminate all this distance here, so by using a datum line. So we're taking the measurements from the datum line this time, which is parallel to x1, y1. So we mark off the distance for A, distance for C, and then the distance for B. And this is our true shape of our triangle. So this is how we find the true shape of a triangle. So first, take a horizontal line in elevation. The reason for horizontal is when you draw it in plan, it's going to be a true length. Then look along our true length, see our triangle as an edge, and then look at 90 degrees to that edge view to see the true shape. So this is the true shape of this triangle. Now we'll have a look at dihedral angles. So this is the first question based on dihedral angles. So a dihedral angle is looking to see the angle between the two laminas, so the two triangular surfaces, to see what angle they make with one another. So that's what a dihedral angle is. So if we look here at the 3D graphic, we'll see arrow B, the arrow points towards B, is we're looking along the edge AB. If we look along that edge AB, which is common to both, we should be able to see the dihedral angle between them. So to do this, we need to find this common edge as a true length. So we need to set up an auxiliary. So our auxiliary is 90 degrees to AB in plan. Now we set up an x1, y1 line, and then we take our heights from our elevation, and now we have a true length for the line AB. And when we're doing this, we'll mark off where C and D are as well. So we mark off the height of C, mark off the height of D. So we have our two triangles drawn again here, but the difference in this view is AB is a true length. Now what we know about a true length already is if you look along a true length, you'll see AB as a point, thus allowing us to see the two planes, or the two laminas, or the two triangles as two lines. So what we have to do now is a second auxiliary looking along AB, set up our XY line 90 degrees to the line AB, and then again measuring back from the previous XY line back for all the points. Now again we use a datum line here to reduce all this distance here to make sure the question fits on the page. So the first point we're marking off is AB. So that's our point AB. We mark off point C and point D, and then we draw our two lines in the second auxiliary, thus giving us our dihedral angle. So this is the dihedral angle between the two lamina surfaces. So this is introducing a bit of colour. So what we'll see here is our two triangles here, two triangles here, two triangles here, and we see an edge view of the two triangles in this question. So key concepts here, what we have to look at is if we have a common edge, this is our line of intersection, we need to see it as true length. So look at it at 90 degrees in one view, so in plan in this case, see as a true length, and then look along the true length to see the dihedral angle. Now in this dihedral angle question 2, the only difference is we have an extra point. So basically it's the same method again. We have a common edge here, so this is our line of intersection between the two surfaces. So we start off with our first auxiliary looking 90 degrees to the line of intersection, seeing the true length. Then we bring up our points, so we mark off our points. So we've each of the points drawn in here, and in this case we, instead of having two triangles, we have one triangle, and then we have a four-sided shape as well. So once we have our true length found, we look along our true length. So what we're doing here is this blue arrow shows the edge we're going to look down along. This red arrow shows it from the auxiliary which direction we need to set up the second auxiliary in. So we're going to look along our true length, so set up a x2 y2 line at 90 degrees. Again using a datum line to reduce distances. We're taking our points from our datum line back the way, and then marking off each of our points, thus giving us our dihedral angle in our second auxiliary. So if we introduce a bit of colour here, so what we have here is the two laminas here, we can only see one lamina here because this lamina is blocking out the yellow lamina, and then this is our dihedral angle view. Now in this question we are not given our line of intersection, so we need to find the line of intersection. So we have two laminas here, red and blue, and they share a common point. Point A is common to both triangles. Now in this question we need to find the line of intersection. So the line of intersection in this question, to find it, we take a horizontal line across in elevation. Now this horizontal line can be drawn anywhere in elevation, but we normally pick one of the points already so that we don't have to find a point. So we're bringing it through point D here, so we'll have point D in plan already located. So in the 3D graphic, this shows what's happening. We're cutting through the two lamina surfaces, and as you can see, when you cut through the two lamina surfaces, it's also cutting through this line here, this line of intersection between the two laminas. So this here is the point that we're trying to find. So what we're going to do here next is bring down this line here, this green line here on the red triangle, and this green line that's on the blue triangle, and draw them lines in plan. We already have them drawn in elevation, but it's just one line in elevation because we're looking in straight at it here, so we can't see the two lines, but we can see the two lines when we project down to plan. So to project down to plan, we mark off 2 points on the triangle ABC, so point 1 and point 2. Bring down point 1 and 2, join them together. Then we mark the next 2 points, so 1 point is point D already, and point 3. And point 3 is on the triangle ADE. So we now want to draw that line on the triangle ADE. So we have D already brought down, so we'll bring down point 3. Join them together. Now we have our 2 green lines in plan, thus giving us our point here. So this is our point on our line of intersection. So now we can draw our line of intersection from point A through this point that we found and extend it until the 2 triangles no longer overlap. So the line of intersection has to stop on this point here. It can't continue on any further because the 2 triangles don't overlap. Now this point here now is on the edge BC, so it can be then brought up on the edge BC and drawn in elevation. Now looking at this question here, we just need to determine what's in front and behind. So in this question here we see D is in front. The reason it's in front is in plan it's the lowest point on the page, so if we were standing where I have the cursor here and looking in at it, D would be closest to you, E would be far away from you, so it must be behind you. So this is how we determine which surface is in front and which surface is behind. And then in the plan view here, again, E is down near the ground, the height of it. C is up in the air here, so that means C is going to be higher, so this is a dotted line in this location here. So introducing the color, then we can see how the 2 triangles intersect with one another, and we have the line of intersection found. Obviously the next section on from this would be to find the dihedral angle for these 2. Now looking at the line of intersection again, this is a second method. Basically the second method is where we do an auxiliary view. So basically we take a line straight across from C this time, see a true length of it in plan, and then look along this true length. Now in this method we're setting up a second auxiliary. I wouldn't recommend this method, I'm just showing students this method would also work for you. So what we have here is, this here is our auxiliary of the triangle ABC, and what we're going to draw next is our other triangle. So what we have here is, this here is our triangle and this is the edge view of the other triangle, thus giving us our point here, which is giving us our line of intersection again. But there's a bit more drawing in this method here because you have to set up a second auxiliary. But then again we introduce the color here again. Now in this question we have 2 triangles that are intersecting one another, so we can see this in the 3D graphic. So this is the line of intersection that we're looking for. Now in this case here we do not have a shared point. So to solve this we need to take a slice across C to find a point on the line of intersection. So to find this point on the line of intersection, we take a line across from C. Then we bring this line down to our plan view. So this is C1. So C1 now is drawn on the triangle ABC. Then we're going to bring down point 2 and 3, which is on the triangle DEF. So 2 and 3 are brought down onto DEF, and these lines are drawn in here. Now this here is a point on our line of intersection. Now in this case here, we can't join it to a common point because they don't share a common point. So we have one point on the line of intersection. What we need to do now is do a second slice across here. So we have a second slice going across here from F in this case. So what I'd recommend in an exam situation to do in this is the first line take across here in a red biro, and the second line take across in a blue biro, so that we don't get confused on which line is which. Now, so to bring down the second slice again, we just number it again. So we're bringing down point 4 onto the edge AB because it's on the edge AB, and we're joining it to point number 6 because 6 is on the edge BC. So in this case 4 joins to 6. Then we have point F and point 5. So we have F already found. We just mark off point 5 on the edge DE and then join them together. Now this gives us our point in plan. So this point is on the line of intersection. So this allows us to join them together and then to extend them until the triangles stop overlapping. So this is our line of intersection. Next, brought up onto our elevation, and you can see in this case it's almost a vertical line. Now introducing color and hidden detail again, we can see how the two triangles overlap. Now once we've done a question basing on finding the line of intersection, this is our full exam question now, where we have to find the line of intersection and then find the dihedral angle. So basically the first thing we have to do here is find our line of intersection. So we take a slice across, so we can see the slicing plane here in the 3D graphic. So in this drawing here, we'll take a slice across from D, which cuts through the two triangles. Then we'll mark these points, bring them down to plan, and then bring down the point from D down to plan, and this gives us this point here. Now in this question both triangles share a common edge, so A, so that means this is our line of intersection found. Bring it up to elevation and we can draw it in. Now this also shows you to do the second method using the auxiliary method. I'll just skip through this quickly here so not to confuse anyone. Now once we have our line of intersection found, we next then need to find the dihedral angle. So the same as previous questions, this is our line of intersection. Look at 90 degrees to it, see it as a true length. So this is a true length up in this view here. Then mark off the rest of our points. So we have points A, B and C, and then D and E also marked off. So we have our two triangles here plus our true length. Now if we see it as a true length, next thing then is to look along the true length and see this true length as a point. So again, setting up a datum line to reduce all this distance here. What we'll then measure from the datum line back the way and find each of the points. So in this case here we have ABC as a line here. Then we may measure for E and measure for D and draw these. This gives us our dihedral angle. Now in this case here, when you're doing this question here, this needs to be a straight line, this needs to be a straight line. If they end up not being a straight line, some measurement along the way from either this view to this auxiliary or from this auxiliary to this auxiliary has gone wrong. So just be careful when you're taking measurements that you measure them correctly. Now this is our dihedral angle. Now to introduce a bit of colour into the question. So this is what the full question looks like. So taking a slice across, finding our line of intersection. Once we have our line of intersection found, then seeing it as a true length and then looking down along the true length. In this question here, we have to find the line of intersection again. So again in this case here, a horizontal cut across from D. So we can see this in the yellow plane here. We can see how it's creating a black line here on the red triangle and a black line on the green triangle. And that gives us our point here. So we have the 2 points marked off here on the triangle ABC, and then we have another point marked off on the triangle ADE. So these points are brought down and marked off, and this is our line of intersection found. And next then, now we'll skip through this here again. If you take a slice, in this case here, we're taking a slice down lower, and what we'll notice here is only cutting through one triangle. So what we're doing here is we're doing the auxiliary method here. So I'd recommend stay away from the auxiliary method because it's extra drawing that you'll have an extra auxiliary on your page and you mightn't have room for it. So once we have the line of intersection found here, next is to find a dihedral angle. So dihedral angle, look 90 degrees to the line of intersection to see if it's a true length. So again, all measurements are found from the previous XY line back the way. So that's how we're finding the heights here for all these points here. And then we have our line of intersection. Now in this case here, we're going to look along our line of intersection. So basically what we have in the 3D graphic here is this green arrow is looking down along the line of intersection, and this green plane here represents what we'd actually see. So we're going to look along this line here. So we're going to look up here because we've space. So x2, y2, then a datum line again, previous view, and measure back the way. So again, we should see our 2 triangles here and see them as 2 lines, thus giving us our dihedral angle. Now this question again, find dihedral angle. So quickly going through it, what we'll notice is there's no shared common edge or common point, so we need to take 2 slices. So we slice through the 2 here, so a slice across here. And draw it in plan, and then draw it. So we have a point here found. Then we'll do the same again here, from C across here, then a line across here. So this will give us a point here. So this will give us this point here. So we've a line drawn across from C here, giving us point 4, 5 and 6. So these points are brought down to plan. Now it is a good technique on your drawing sheet to draw these in blue biro for one of the slices and red biro for the other slice, so you don't get them mixed up. So we draw this line now in plan, projected up to elevation. That's our line of intersection. Thus to find the dihedral angle, then we need to look along our true length. So to look along our true length, We have our true length in plan, so look 90 degrees to this line of intersection in plan to find our true length of our line of intersection. So this is our two triangles drawn the first auxiliary, and then our line of intersection. So this is our line of intersection, which is now a true length. So if it's a true length, if we look down along it, we need to see it as a point view. So we're going to look this along as a point view now. So this will give us triangle ABC as a line. Next we'll find triangle DEF. So DEF, this case here, D, point E, and then point F. And then what we have here is our dihedral angle now found in this question. And this is introducing a bit of colour here to show how they're intersecting one another, to make it a bit more clear for us to understand. Now we look at a higher level question from 2009. So this is a standard Leaving Cert higher level question. So what we're given first of all is all these coordinates here. So the coordinates here is 145, 80 and 30. Now how we represent these on a page is the first one is the X axis, then we have the Y axis, and then we have the Z axis. So the X axis is horizontal, Y is up and Z is down. So when we want to measure this on an XY line, we start off somewhere on the page, a red line here. So this here is our reference point, and then our red line going across here is our XY line as we know it in orthographic projection. So from this point here we measure across 145, then we measure up 80, and that's point A in elevation, and then we measure down 30 in plan, and that gives us our point in plan. So it's the same process then for point B, over 125, over 105 or 205 from the edge here, and up 35 and down 70, and so on with all the rest of the points. Again, in the triangle DEF is done the same method. So DEF is done the same method here. So we have our two triangles set up here in both elevation and plan. Next we need to construct how we're going to see the method of the line of intersection. So first method here that is shown is looking at the auxiliary method. If we take a slice looking along one of the edges here, and then finding this view here. Now this is one method to do it. The preferred method that I'd prefer people to use is to use the horizontal method. So using cutting planes that cut across. So this method here, we take a line across from A, and what we notice in this question is A and C is horizontal. So that means this is a horizontal edge, so that means this line is already drawn in plan. What we need to find is take 2 points now on the triangle DEF. So this line now that's on DEF, we draw it now in the plan view. So we point 1 and point 2, and we can draw this line here. This gives us our point on the line of intersection. Now in this question we take a second slice. So in this case here, we take a slice across from F, and then repeat the process. So what we have is point 3 and 4 on the triangle ABC, drawing this line, and then find point 5 on the triangle DEF, join it to F. That gives us our second point here, and draw this line joining up the two dots that are on the line of intersection, and then extending them then until the two triangles no longer overlap. So this here is our line of intersection in plan. We bring it up to elevation. So this is our line of intersection. Now, to draw the dihedral angle then, we look 90 degrees to this line to find the true length of our line of intersection, setting up our two triangles in our auxiliary view, then finding our line of intersection. So this is our line of intersection now, seeing it as a true length. Now, next we look along our line of intersection. Once we see it as a true length, so we see this blue arrow here looking up along onto this plane here, so projected up onto this green plane now is what we see when we look along a true length. So it's the same here. We look along this true length here, and we'll see the line of intersection as a point view. So again, we set up our datum line to reduce all this space here to make sure this drawing fits on the page. So we have triangle ABC found, and in this case here to find triangle A or DEF. So DEF is found in this location here, and then we mark off our dihedral angle. So this is our dihedral angle now found. Now in this question here, we're asked to find the true length or the true shape of the triangle ABC. Now the reason we need to find the true length of the triangle ABC is what they want us to do in this question is to draw an offset triangle in 10 mils on the triangle ABC. So we need to measure in 10 mils from the edge here and from the edge BC and AB. So this is to represent a set square. So in order to do this, the easiest way is to see this blue triangle as true shape, and then we can mark in our 10 mils all the way around. So what we have to do in this case here, first of all, see this triangle as a line view. So to look along a true length, so AB or AC is level in elevation. That means it's a true length in plan, so we look along it, we see AC as a point and then B is a point. So we can draw our triangle here. Now look at 90 degrees to this, marking off our triangle ABC. So we now have the triangle ABC marked off. What we're asking the question is to measure in 10 mils and draw this inner triangle here. Now this inner triangle here, we're brought back to the previous view. Then these two lines are brought back, then measurements are took from the previous XY line and marked off. So again, this is marked off in plan, then brought up to the elevation by measuring to the previous XY lines. Now this here is a higher level question again from 2010. So this question here is a relatively easy question because we have two triangular shapes here. So we have a blue triangle, red triangle, but in this question here we're actually given the line of intersection, so we do not need to find this line of intersection. So what we know already is look 90 degrees to the line of intersection, see it as a true length. So now we have a true length of this line of intersection. So if we look along the true length then, see it as a point view. This gives us our dihedral angle here. So our dihedral angle in this case is almost almost 180 degrees. In this question they want us to see the true shape of this triangle here, ABC. So they want us to get the true shape of this triangle here. So the easiest way to do this here is draw an auxiliary. AC is level in elevation, so that means it's a true length and plan. So if we project an auxiliary looking along AC, we see it as a point. Then B is height found in elevation brought onto auxiliary, marked off in this location here. So this here is an edge view of this triangle. Now what we're doing in this case here, rather than looking at 90 degrees to this, we're using the edge AC as a hinge. So we're using AC as a hinge here, and we're folding down B. So we're folding B down onto the ground. So we have it now found flat here. So what we're doing here is bringing B straight up here and drawing the true shape. So this is the true shape of this triangle ABC for this question here. Now an alternative method of doing this is taking this edge view here and looking 90 degrees at it using a second auxiliary. So this is probably a method that we're used to, marking off our measurements here. So this here is our true shape of our triangle here. Now in this question here they also asked us to show the traces. So what we're doing to find the traces of these triangles here, basically in the 3D graphic here, we're taking the line of intersection here, using that as an edge and running that edge into the ground to find this point here. So what we look here, we also take another line on the edge BC, extend it until we hit it into the ground. So to show this in elevation, we extend this edge here AB into the ground, bring it down to plan, extend AB in plan. That gives us a point on a horizontal trace. Then we repeat for the other side. So our edge BC, extend it, and then draw our horizontal trace. So this is our horizontal trace now located. Now to do the vertical trace, we're going to extend on the edge BC this time until it hits the XY line. Now when it hits the XY line, if you imagine this XY line also as the back wall, so we've ran AB into the back wall here, so we're going to extend AB in elevation and then bring it straight up. This here now is a point on our vertical trace, and we can draw a vertical trace level here because it needs to be parallel in this case, because if we look at the 3D graphic here, if this horizontal trace is level or horizontal in plan, our vertical trace is going to be horizontal in elevation. That concludes. We'll look at the exam questions now in a small bit more detail. So we've looked at two of these questions already. So this question is where we have the two triangles and they share a common edge. So in the question here, what you're shown is a sculpture that's made up of intersecting triangles, and what you're given here is the coordinates. So what we notice in this, it's triangular surface planes ABC and ABD. So we first of all set up these points on a sheet. So we get marks for drawing part A. Then part B is determine the dihedral angle between the planes. Next, find the true shape of the triangle ABC, and then finally determine the traces for the plane that contains triangle ABC. So we've looked at all that in the video, but this is how it's shown in the exam paper. Now question 2, we have this question here. So we've looked at this in detail on the video already. So this here is what it looks like in the exam paper. So what we have here is given a 3D graphic here showing what's representing two interlocking set squares. So these are all the coordinates given to you here. Next is the questions. A, draw the plan and elevation of the intersecting planes. B, determine the line of intersection between the planes. C, determine the dihedral angle between the planes. So you'll notice that they've broke it down into 3 steps here. So step 1 is just draw the 2 triangles. Step 2, determine the line of intersection. Step 3, determine the dihedral angle. Now part 4 here is the internal triangle is a 45-degree set square ABC. Is offset 10 mils from the outer triangle. So we've looked at how you do this. Draw the plan and elevation of this internal triangle. So what we said how to do this is, if we see triangle ABC as a true shape first, then we can measure in our 10 mils and then bring it back to our other 2 views. Now the third question here that I haven't gone through in the video yet is this structure here. So this structure here, instead of having triangles this time, what we have is we've polygons here showing this 4-sided shape here, this 4-sided shape here. So the first part of this question is just draw elevation and plan of the 2 intersecting planes. So straightforward so far. Second then is determine the dihedral angle between the planes. So they're not looking for a line of intersection because we should already know the edge AB is common to both. So this here is your line of intersection. So we need to look 90 degrees to this line of intersection, then see it as true length, and then look up along it to find our dihedral angle. Next part here, determine the true shape of the surface ABC. On the true shape then include a 20 mil circle for a porthole given that the center is 30 from the line AB. So it's 30 away from the line AB, and then it's 50 mils from the point D. So from the point D, so obviously we'll be setting 50 on our compass from point D and scribing an arc. So we have to see the surface ABCD as a true shape. So we've looked at how to do true shapes already, so this shouldn't be of any great difficulty. Next part then is part D. The midpoints of the lines AB and AD and AF are defined an oblique plane which contains the seat. Draw the elevation and plan of the seat. So what we have to do here is AD is on the ground. So we have a point here. That point is easy found. It's midpoint. So if we bisect this line, we find this point. And it's the same with the point here, A to F. If we bisect this line, find this point here. That's easy to find. The only issue is how do we find the midpoint for on the line AB? Now my suggestion to find that, and the easiest way I find of doing this, is imagine B is the top of a cone, A is the base of a cone. If you were to draw the plan of the cone, so from here, from A here, draw an arc out to the side here, bring this point, bring a level line across then from B, in elevation draw this cone again. What this gives us is, it gives you the true length of the side of the cone. So if you bisect that line, it's a matter of bringing this point straight in. Now that allows you to find this point. Then we just construct your 2 lines, up 5 mils, a line across here then for the seat. Now the last part of this question that some students do not see, and it costs them a few marks, is determine and indicate the horizontal and vertical traces of the oblique plane. So that's for the seat, for this section of the seat here. Now what we should know is, if we think about this already, they've extended on this line here onto the ground here. So this here is a point on the ground. This is also a point on the ground for the trace. So if we connect these 2 points already together, that's our horizontal trace. And all we do then is take another point here, carry parallel to our horizontal trace, bring it up across, and we can find the vertical trace very easily. So these are the questions associated with this video. 3 straightforward intersecting planes questions.